Hey, welcome. Today, we are diving into a really cool puzzle that's kind of hidden in plain sight all around us. Think about the internet cables running under our streets or the power lines crisscrossing the country. Let's get into it. Okay, so picture this. You've got a bunch of points you need to connect. It could be cities on a map, servers in a data center, or maybe even houses in your neighborhood. The goal is to link every single one of them together. But here's the catch. You're on a tight budget. So how do you build that network using the least amount of cable or road or whatever it is you're using? I mean, if you just start connecting things at random, you're going to end up with an absolute mess. It'll be tangled, inefficient, and crazy expensive. You might have 3 different roads between the same 2 cities, or all these weird loops that go nowhere. So the real trick isn't just about connecting everything. It's about finding that one single, most efficient way to do it.
And lucky for us, that elegant, super efficient solution actually has a name: the minimum spanning tree, or MST for short. So let's break down what that really means.
First off, let's just talk about a spanning tree. Forget about the cost for just a second. A spanning tree is basically a network that connects all of your points, we call those vertices, using the absolute bare minimum number of connections, or edges. And here's the most important rule. It has absolutely 0 closed loops or cycles. Think of it like a skeleton network. No fat, no redundancy, just pure, simple connectivity.
Okay, now for the fun part. In the real world, not all connections are created equal. Building a highway through a mountain is way more expensive than building one across a flat prairie. So, to account for this, we give every possible connection a weight, which is just a fancy word for its cost.
And when you put those 2 ideas together, you get the main event, the minimum spanning tree. It's a spanning tree, so it connects everything with no loops. But it's the one specific version where the sum of all those weights, the total cost, is as low as it can possibly get. It is, without a doubt, the cheapest way to connect everything.
So how do we actually find this thing? I mean, you can't just guess, right? For a network with just 10 cities, there are over 100 million possible spanning trees. There's no way you're going to find the cheapest one by trial and error. Thankfully, computer scientists have come up with some brilliant and actually pretty simple ways to find the perfect MST every time.
Our first method is called Kruskal's algorithm, and I love this one. You should think of it as the ultimate bargain hunter. It has one super simple philosophy: always grab the cheapest deal available on the table.
So how does our little bargain hunter work? Well, it's really methodical. First, it makes a list of every single possible connection you could make, and it sorts that list from the cheapest to the most expensive. Then, it just goes right down the list, one by one, grabbing the best deal it sees. There's only one rule. It will not take a deal if that new connection creates a closed loop with the ones it's already picked. It just keeps grabbing the next cheapest option until, boom, everything's connected.
Okay, let's actually watch this thing in action. Here are all our possible connections, sorted by cost. Kruskal's algorithm takes one look at the top of the list and immediately snags the cheapest one there. That's the link between D and E, with a tiny cost of 1. Easiest decision all day.
All right, moving down our list. Next, we see 2 different connections that both cost 2, one between A and B and another between E and F. So the algorithm has to ask itself that all-important question for each one: if I add this to my collection, am I accidentally creating a cycle?
And the answer is, nope, no loops are created. So it adds them both. And what's really cool here is how the tree is being built. See, Kruskal's doesn't grow out from one spot. It creates these little disconnected islands of cheap connections, which we know will all get linked up in the end.
And here it is. This is where we see that crucial rule in action. Later on, the algorithm gets to the edge between B and E. It's the next cheapest option. But wait, look what happens if we add it. We could now go from B to A, then to F, then to E, and whoops, right back to B. That's a closed loop, a cycle. So the algorithm says, nope, can't do it, and rejects that edge, moving on to the next one on the list. It's pretty smart.
Okay, so that was Kruskal's, our bargain hunter. Now for method number 2, Prim's algorithm. And if Kruskal is zipping all over the map grabbing deals, Prim's is more like an empire builder. It starts in one place and strategically expands its territory, one connection at a time.
Prim's has a completely different game plan. You start by picking any single city, just one. That's your capital. From there, you look at all the roads leading out of your current territory and you build the absolute cheapest one to a new unconquered city. Now your empire is 2 cities strong, and you just repeat that process, always looking for the single cheapest bridge from anywhere inside your borders to the outside world.
All right, let's run the same puzzle, but this time using prims. We'll just randomly plant our flag at City A to start. From this single point, the algorithm sees only 2 possible moves. It can build a path to B for a cost of 2, or it can build one to D for a cost of 6.
The algorithm's logic at every step is dead simple. It looks at the frontier of its current empire, which right now is just City A, and it asks one simple question. What is my absolute cheapest path to expand my territory and connect to somewhere new?
Well, between a cost of 2 and a cost of 6, that's a no-brainer. The algorithm builds the bridge to B. Now here's the crucial part. Our empire now includes both A and B. So for the next step, it looks at all the paths leading out from both cities to find the next cheapest expansion.
So let's put these two head-to-head for a second. Kruskal's is edge-based. It looks at all the possible deals at once. It's our global bargain hunter. Prim's is vertex-based. It grows from a single connected area. It's our local empire builder. And because of these different approaches, they actually use different tools behind the scenes, which makes them better for different types of graphs. Kruskal's tends to be faster for sparse networks where there aren't a ton of connections, while Prim's usually has the edge on dense, really tangled networks.
Okay, so we've got these 2 really clever algorithms, but why does this matter? Why is this useful outside of a computer science textbook? Well, let's take a look at how this abstract idea actually builds the physical world around us. The applications are, and I'm not exaggerating, everywhere. Anytime you need to connect a bunch of points with the minimum possible cost, you're looking at an MST problem. We're talking about laying fiber optic cables, designing a power grid, planning out a network of water pipelines. It even shows up in computer science for designing efficient circuits on a chip and for clustering data and machine learning, grouping similar things together in the most logical way.
What is just so amazing about both of these algorithms is that they're considered greedy. All that means is that at every single step, they make the choice that seems best at that exact moment. They pick the cheapest available edge without thinking about the future. Now, in a lot of complex problems, that kind of short-sighted strategy can lead you to a really bad overall result. But for finding a minimum spanning tree, it's like magic. It works perfectly and is guaranteed to give you the absolute best global solution.
And that leaves us with a pretty fascinating thought. This problem proves that sometimes a series of simple, locally optimal, greedy decisions can perfectly solve a massive, globally complex puzzle. It kind of makes you wonder, doesn't it? What other huge challenges out there could be solved not with some grand, complicated master plan, but by just making the best possible choice at every single step along the way?